Greetings, dear participants. I'd like to present you our research thermal image super-resolution methods using neural networks. Thermography has gained popularity in many fields. Since the human eye cannot see the thermal spectrum, thermal image analysis has become an integral part of medicine, manufacturing, construction, and other industries. It is widely used in medicine for abnormal body temperature detection, breast cancer diagnosis, and for detection of other diseases. It is also used in architectural and civil engineering, manufacturing, electrical engineering, and for field phenomics. Despite having a lot of applications in different fields, thermography has its own drawbacks. The main issue with thermal images is the resolution of the output thermogram. Besides, thermal cameras that can produce high-quality thermograms cost much more than regular cameras and are not affordable to ordinary users. This creates a need for thermal image super-resolution methods. The purpose of this research is the implementation and analysis of different modern super-resolution methods in the thermal image domain. This work has following objectives: analyze existing super-resolution methods, choose neural network architectures, choose metrics for evaluation quality of models, conduct experiments with chosen models in thermal vision domain, and analyze the results. The formal problem statement is the following. Given an original thermal image and its downsampled version, the task is to create a model that has a maximum value of metric on original and upscaled thermal images. For metrics, structural similarity index measure and peak signal-to-noise ratio can be used. Super-resolution methods can be divided into several groups: interpolation methods, convolutional neural networks, generative adversarial networks, and transformers. Each of these methods has its own advantages and disadvantages, but in practice, neural network-based methods show better performance, which usually overlaps their disadvantages. Interpolation methods are the simplest among all super-resolution methods. Among them are nearest neighbor interpolation, bilinear interpolation, and bicubic interpolation. These methods are the fastest of all. Despite their ease of implementation and clarity, the main disadvantage of the interpolation methods is the quality of the output image. Convolutional neural networks have comparatively high quality of results, and they are easy to train. Generative adversarial networks use architectures that consist of two networks, generator and discriminator. These networks can achieve good results in image upscaling, but they are hard to train. Transformers use attention mechanism that helps model to focus more on special parts of image. These models can achieve good results in image upscaling, but they are also hard to train as they require a lot of training data. Since the task of thermal image super-resolution is quite specific, the number of open source datasets for this task is quite low. One of the largest and most popular is the FLIR dataset. This dataset offers annotated thermal and RGB images for the detection systems. The dataset contains almost 10,000 thermal images. One of the most popular datasets for solving the RGB super-resolution problem is div2k. This dataset contains 1,000 high-resolution images. In this work, both of these datasets are used. In particular, div2k is used to examine the performance of model trained on grayscale images of this dataset in thermal image domain. For experiments, several models of different types were chosen. All models were trained for 100,000 iterations. The number of images in one training batch is 16 and 64 for different models. Adam was chosen as an optimizer for all models. All models were trained not on whole images, but on square patches that were randomly cropped from each image. This speeds up training and forces the neural network to pay attention to high-frequency features. From the obtained results, it can be concluded that SwinIR transformer trained on a FLIR dataset shows the best results among other models. Additionally, according to the results, CNNs are better than the whole GANs. It is also visible that SwinIR trained on FLIR dataset performs better than SwinIR trained on grayscale diff2k dataset. As it can be seen from the qualitative results, GANs have a lot of noise on the upscaled images, which causes bad quantitative results, while CNNs and transformers almost completely denoise upscaled images. It can be explained by the fact that GANs are sensitive to the input data and selected training hyperparameters. The main problem of this task is the lack of datasets for the thermal image super resolution. Current datasets don't have enough training data. The size of thermal images in datasets is not as big as in RGB datasets for super resolution tasks. And quality of thermal images is worse than quality of RGB images in training sets. According to the obtained results, the thermal image upscale, it was concluded that transformer and CNN models could perform better than GANs and classic algorithms. In addition, the following steps can be taken to improve the quality of the super resolution of the thermal images. Firstly, increase the size of the dataset and training batch. Collect dataset of thermal images with high quality. Tune training hyperparameters such as optimization algorithm, learning rate, loss function, etc. Improve the architecture of used models or modify them for the task of thermal image super resolution. Thank you for the attention.